when we talk about a through fault monitoring for power transformers, basically what we're trying to avoid is what we categorize as mechanical failure in your transformer. And when you try and look at transformer failure categories, there's basically only three. There's electrical, mechanical, and insulation failures. And mechanical failures basically involve the physical displacement or damage of parts within the transformer. And this can happen for several reasons. And of course, the one big one that we know about is when you purchase a brand new transformer and it's being shipped from the OEM and they load it on a rail car or on a flatbed. And of course, any transportation mode can cause a shock or vibration that can actually damage the windings of the transformer and the internal structures. And this is why we put shock monitors, sometimes vibration monitors on transformers when they're being transported. But they can also happen from seismic activity if you have in a high earthquake area for a GSU or generator step up. If you have improper synchronizing, this will cause mechanical forces on the windings that will cause failures. But what we're going to concentrate on today is what we call through faults. So we know that power system faults external to the transformer zone can cause high levels of current flowing through the transformer, and that creates forces within the transformer that can eventually weaken and damage the winding integrity. A comprehensive transformer protection scheme, this is your protective relay system, or maybe even a transformer monitoring system, should be able to have or should have the capability of monitoring the through faults that happen while the transformer is online over a certain given period of time. If we look at a typical protective relay system, you'll notice we have two different categories of protective elements for transformer protection. One which I call the proactive, and some which I call reactive. Now, proactive transformer protection consists of things that will protect the transformer from conditions that happen out in the system. Things like overvoltage condition, or a volts per hertz condition, which can cause overheating, or frequency excursions that could damage the transformer. Anything external to the transformer itself that could possibly damage is what I would call a more of a proactive relay system for the transformer. Now, there are some called reactive, things like sudden pressure relays or Buckholz, or what we know as a 87 or current differential, which will detect any fault within the windings of the transformer and eventually, of course, or hopefully immediately take the transformer offline to prevent further damage or, God forbid, catastrophic failure. The thing with that is, and why I call that reactive, is because if you have a differential trip on your transformer, chances are the damage is already there. Okay, what we're trying to do is just limit the damage at that particular point. So the one thing that we have to know about a through fault condition is that it's really not something that can be protected against using differential protection. And why is that? Well, a through fault is just that. It's a fault that's going through the transformer. The fault is either in the system, either after or before that protective zone of these CTs. Now, remember, a differential protection only senses faults that occur inside the range on these CTs, on both the primary and the secondary windings. So it's not going to see a fault necessarily that is external to the transformer itself. For this, we use, okay, if it's a transmission system, we use things like a distance or line differential relays or some type of overcurrent protection scheme that should clear a fault. However, the problem associated with that is the fault has already occurred, and that through fault has already gone through the transformer itself. So if we look at a simple diagram right here of a generator, transformer, and then a transmission line, you can see that we can have faults on either side of the transformer that is not necessarily protected by the transformer's relay system. And you really wouldn't want that to happen, because there are excursions that can happen out in the system that is a momentary fault, that you wouldn't necessarily want to take the transformer offline if it happened. You want your protective relays that are, not necessarily protecting the transformer, but your transmission line or your feeder, to go ahead and clear faults that happen. But unfortunately, by the time that happens, it's too late, because that fault has already passed through the transformer. Um, and it's important to know that the damage that can occur on a transformer from a through fault depends kind of on how the transformer is designed. And we know that through faults are more damaging to core form rather than shell form transformers, just because of the design of a shell form has multiple current paths, and it kind of absorbs that mechanical shock. That doesn't mean that we shouldn't be monitoring through faults on a shell form transformer. A significant through fault can still create damage. It's just not as likely to occur. So through faults can vary greatly across short spans of any electrical grid, and factors such as circuit length, the circuit type, whether it's overhead or underground, the protective equipment, the infrastructure, the terrain, all these things have to be taken into effect and into consideration as a means of creating a through fault on the system. But they're generally the result of a low impedance path to ground being introduced into the circuit, such as dielectric failure of protection equipment. It could be tree limbs and distribution striking overhead lines, causing the current to exceed the transformer's base rating. And that's really what we can have to be concerned about. You can have you can have a slow or malfunctioning circuit breakers that, in case there is a fault, that the intensity of that fault and the magnitude and the duration of that fault can be much greater if you have a slow or malfunctioning circuit breaker on the system as well. So if we kind of look at how a through fault monitor works, and most all of your protective relays nowadays, your modern protective relays have through fault monitors. And I was having a discussion with a good friend of mine that works for Schweitzer. And one of his specialties is transformer protection. And I had a discussion with him about through fault monitoring and what Schweitzer does in terms of making that available to their customers. And he said, "Yeah, Drew," he says, they all have through fault monitors." He said, "But very few customers actually set it and enable it on their transformers." And it just makes me think there sometimes is that disconnect between maintenance crews that work on transformers from a maintenance standpoint, and those that actually set the protective relays, or the relay engineers. So we have to kind of bring these two disciplines together to make sure that we're doing an adequate job monitoring and measuring through faults that happen on the system. So this is just a simple logic diagram where the relay is looking at a cumulative I square T value on each of the phases, and it compares it against a threshold that we set in the relay. And that threshold has to do with the mechanical withstand capabilities of that particular transformer. And that's based on size and rating and all different types of variables. But it records the values to assist your substation crew in prioritizing maintenance and testing. And this is what's important, because if you've had through faults, or you've recorded a series of through faults on that transformer between maintenance periods, it might be a good idea to test for any possible mechanical or structural damage internal to the transformer. But over time, these recorded values provide additional information, also in determining potential problems within in the transformer itself. So this is an actual recorded event, and I apologize for it being fuzzy. It was taken a screenshot off a PC, but your through fault occurrences within a given period of time can indicate a need for maintenance, such as tree trimming or right-of-way clearance. And this little illustration shows three things that are very important in terms of through fault. The date and the time, of course, that the through fault happened, but the magnitude in terms of times of the base rating of the transformer itself, the duration of how long the through fault occurred, and the number of occurrences that it's had. So three things that we want to be cognizant of in terms of a through fault. And the reason is that not one particular through fault is going to necessarily cause immediate damage, but it could come from a number of or a series of through faults that have occurred over a period of time. So those are the three parameters that we want our through fault monitor to be able to tell us. So how do we determine the settings for a through fault? Now, remember, a through fault monitor is not going to take the transformer offline, but it can set to give you an alarm or give you an alarming indication that these have occurred if they are, again, happen enough times, a long enough duration, and the number of base rating in terms of what that transformer can withstand. And this comes down to basically being able to categorize your transformers. And of course, we all know there's like 4 categories of transformers based on the kVA rating. So this is the first thing that's important to know. And again, we're talking about liquid filled transformers, oil filled transformers, and that doesn't mean to say that through fault monitors can't be applied or through faults can't damage a dry type transformer. They certainly can, but your biggest expense and your cost and your concern has to do with your oil filled transformers. So to provide a bit of a more comprehensive representation of the long-term effect of system conditions on power transformers, each category includes its through fault capability limits. And this can be, you can have a program that can help you calculate exactly what you want to create these settings to be. And a lot of this will have to do with the maximum current and per unit of the base rating of the transformer. And that has a lot to do with the transformer's short circuit impedance for both category 1 and 2. Okay, so the smaller transformers, we're going to work with the short circuit impedance, and then the maximum current calculation for category 3 and 4 transformers is based on the overall impedance of the transformer's short circuit impedance and system impedance. So if there's any doubt in terms of how you want to set this, it's good to always refer to the transformer OEM for this information. So if we look at the different types of transformers that we have here, the different categories, you'll see that these setting curves all kind of look fairly similar, where down on this lower section we have the multitude of or times the base current rating of the transformer, and then the magnitude or the length of that through fault that has occurred. So basically, if you exceed these values right here based on the times base current or the time in seconds, that will trigger your through fault monitor to trap and record that information and possibly give you an alarm. So when in doubt, in terms of how to set and what to set your values at, it's always good to refer to your transformer manufacturer. So let us say that we've had a number of through faults and our through fault alarm has gone off a number of times, and we're not sure if we have had any mechanical damage done to the transformers at any given time. There are 2 basic tests that we want to do, diagnostic tests for mechanical failure. One I'm sure that most of you are familiar with, and that's sweep frequency response analysis. And this is part of IEEE C57149, and this is a guide for the application and interpretation of FRA. This is currently under revision, and there's some new information that is soon to be released by the Transformers Committee in terms of better evaluation information and some better techniques in terms of different types of transformers in terms of testing. And then for leakage reactants, that's part of C57152, and that's the guide for diagnostic field testing of fluid-filled transformers and reactors. And I always like to go back to these resources in terms of guides, because the work that goes into developing these standards for people to use in the field is quite intense and very well thought out by factory experts. So SFRA, this has been around quite a while, and this is a method to evaluate the mechanical integrity of your core, your windings, and clamping structures within the power transformers by measuring their electrical transfer functions over a wide frequency range. And what we're going to be looking for is any core movements or faulty core grounds, winding deformation, winding displacements, partial winding collapse, hoop buckling. You can see there's a lot of different scenarios where you can have mechanical failure. And here in the picture, you can see some of these illustrations. Now, how does a SFRA work? I always kind of equate it to a fingerprint, okay? Because transformers, they typically generate a unique signature when they test at discrete frequencies, and they plot these of a curve. And the distance between the conductors of the transformers forms a capacitance, and any movement of the conductors or windings are going to change this capacitance. And that's, again, part of a complex LRC circuit or RLC circuit or network. And any change in capacitance will be reflected in the curve of the signature we get in our response. So changes in the frequency response can be compared over time and, between test objects or within the test objects. But the one important thing, and I always make this recommendation, if you're buying a new transformer, one of the things you want to put into your purchasing specification is to make sure at the factory, before they ship that transformer to you, to get an SFRA baseline. Because again, any transportation that occurs can cause some mechanical shift during that process, especially if it's going on a rail car. A rail car is the hardest, because from transporting from the factory to your location, it's going to be, coupling and decoupling cars, and any of that excessive movement can create these mechanical failures. So starting with a baseline is always very important. Now, SFRA is a low voltage, non-invasive test done offline, where we have an output signal and a reference channel, and then a measurement channel that we're going to use to get our measurements. And this is a typical measurement setup for a delta Y transformer, and you can see the fairly simple connections. Now, the thing about an SFRA, it's not just one single test. It's not like you're going and doing just one CHL measurement like you would maybe if you're doing power factor. But for a typical delta Y transformer with a 30-degree phase shift, 2 winding, you'd have actually 9 different tests to run. And consider it like a chest x-ray. If you go to the doctor and he's ordering a chest x-ray, you're going to go from front to back to front, one side to the other. Okay, this is kind of the same thing that we're doing with SFRA. What we're really doing is we're comparing the signals from the high side to the low side on each phase, the low side back to the high side, and then the high and the low side to ground. So it's important that you cover all recommended tests for the type of transformer and how it's configured. Again, based on IEC C57149, this guide gives you all the connection diagrams, as well as your test set manufacturers can guide you through this process. But you'll notice here we have 3 different categories of tests. We have a high voltage open circuit test, a low voltage open circuit test, and then a short circuit test. So it's important when we're testing, doing SFRA, to really thoroughly look for any damage that may occur, to do all recommended tests associated with that type of transformer. So what do we get in our results? Well, depending on the range and the measurement area, in this lower frequency range, we're going to look primarily at the core of the transformer. We're looking for any core deformations. And then in that mid-range, we're looking at the interaction between the windings, between the primary and the secondary windings. And then in the upper range, the winding structure influences. So the results on an SFRA can, yes, it could verify that you either do or do not have a noticeable mechanical failure, but it'll also tell you kind of where that failure is located. Well, the one thing we know about through faults and any high current fault in a three-phase core form transformer is generally associated with the results you get in the low voltage winding in the form of radial deformation. So their diagnostic focus for through faults will be given to the low voltage open circuit and high voltage to low voltage short circuit responses. And this is in the guide, in the IEEE guide. Documents it documents both open circuit and high to low voltage short circuit responses. So this is typically where we see any deformation that has been a result of a high through fault on a transformer. Okay, so the second diagnostic test, and this is typically overlooked because I don't know that people really understand why we do this test, and this is called the leakage reactance test. It's also known as a short circuit impedance test. And we do this to detect any mechanical winding movement or deformation within a power transformer. And there's basically two methods of performing the leakage reactance test. And one is the three-phase equivalent test, and the other is a per-phase test. And basically what we're talking about here is is looking at the actual overall impedance of the entire transformer as a measure of looking at leakage flux. Now, when we talk about flux, think of it this way. Think of we have a trough with water running downhill. It's an open trough, and naturally during that water flow, some of the water is going to spill over, and we're gonna lose some, right? Well, flux is kind of the same way. Well, say somebody comes along and they take a big rock and they put it in the middle of that trough, and it starts to spill over even more. Well, that's kind of what we're looking at here, and we're measuring this leakage flux by looking at impedance. Now, whenever you're doing diagnostic testing of a transformer, it's so important to become very familiar with the nameplate of that transformer. And on that transformer, what you're going to find, and it's stamped right on the nameplate, is what the impedance percentage was at the factory at the time of manufacturing. Okay, and this is important to know because what this represents in the transformer is normal leakage flux in the core, in the windings of the transformer. Okay, so when we do a three-phase equivalent test, and this is your test connection sequence, and again, this is an offline, fairly non-invasive. Okay, basically, they used to refer to this as a short circuit impedance, or a lot of people still do, because basically we're going to short out our bushings. And you can see here to do a three-phase equivalent, we're going to short X1, X2, X3, and we're going to measure H1 to H3, H2 to H1, and H3 to H2. And what we're going to do is we're going to take the results of those measurements, average them together, and get our three-phase equivalent. But then we want to go one step further. Okay, we want to measure the impedance per phase on each individual phase. And again, this shows you the connection diagrams that are important to follow when you do this. And by the way, and I'm going to make a mention of this, I'm not sure how many of you actually go out and test transformers. I hope that's the majority of our audience. Whenever you short bushings to do dielectric testing or any diagnostic testing, you want to make sure you use a number 4 gauge bare copper wire with good clamping force on those bushings to make sure you're getting accurate measurements. I see a lot of people out there with insulated jumper cables or braided copper or, all sorts of, thin wire to tie those bushings together. Not acceptable. Please make sure you use a good number 4 or number 6 gauge bare copper wire with good clamping on there to perform these tests. So these are the 2 series of tests that we're going to do when we do a leakage reactance test. So basically on our 3-phase equivalent, what we're doing, and this is the formula that actually averages the 3 phases together and calculates the impedance measurement of the entire three-phase structure. And then what we're going to do, and you'll see down here in your delta Z, is we're going to compare the measured value to what's on the nameplate. Okay, and that's important because we have to see what that delta is to determine whether or not there might be some kind of physical damage or an increase in those losses. Okay, again, measured in terms of impedance. Now, the purpose of the three-phase equivalent test, this is to produce a test result to compare the factory short circuit impedance in percentage, which can be found on the nameplate. Now, IEEE standards and ANSI standards tells us that that measurement should be no greater than 3% between what you measure and what's stamped on the nameplate. Okay, now, similarly, when you do your per phase measurement, the phase A, phase B, and phase C should all be within 3% of each other as well. Because as we can see in an example I'm about to share with you, you can have a three-phase equivalent measured at less than 3% deviation, but in one of those three phases could greatly exceed 3%. Excuse me. So here's a case study that I like to share. This is a transformer that had a series of through faults, okay, 50 MVA transformer, DY1. And then what happened was the differential relay was tripped and took it out of service. And there seemed to be some oil leaking from the de-energized tap changer on the low voltage side. And, you know, whenever you get oil leaks somewhere, pay really close attention to that. Not only does that mean that you could have a potential problem with the windings of the transformer, but anytime mineral oil is coming out of the transformer, moisture is coming in. And three things that kill the insulation of a transformer more than anything: moisture, heat, and oxygen. Okay, so pay attention if you've got a leak, a leaky gasket in your transformer. So what we did here, after the relay tripped the unit offline, is, you know, whenever you're trying to figure out what's happened to a transformer, it's not just one particular test or maybe even one or two tests. It's a series of diagnostic testing that you're going to go through. Okay, so what do? Well, a relay trips the transformer offline. The first thing you're going to do is you're going to pull a DGA, oil sample, and you're going to send that off to the lab for analysis. Then you're going to disconnect all your leads. You know, put up some scaffolding or get your ladder out and, you know, get your power factor test set out and start measuring power factor. Well, that was the first thing that we did on this transformer, and it wouldn't even run on the low side at 10 kV. And we had to lower the voltage down to 7,000 volts, and the power factor was almost 50%, and, you know, on the CL insulation, and that is clearly unacceptable. That's a major, I got a problem. Okay, and again, this thing had been exposed to significant through fault. The next is your DGA results, and this is a telltale right here, because you'll see in this illustration along the red here, you'll see the dates of the samples. And of course, anytime you're doing this, you're going to have historical information, because that's always important when you're doing testing. But you'll see our acetylene jumps right up from 0 up to 21, and this is a major indication that we've got an extreme heating situation going on in the transformer. Okay, so first two tests, we don't know what it is. We don't know necessarily where it is. Okay, but we do know that we have a serious problem. Okay, so next is the leakage reactance. And this is important to see right here, because what you're going to see is that when we did our three-phase equivalent, our delta between what we measured and what was on the nameplate is only 2.85. So that's well within 3%. But when we look at our per phase measurement, we'll see that B phase, that's where our problem is. We have a problem on the B phase winding. Okay, so that is clearly an indication that we've had a fairly catastrophic failure in the transformer. So if we look at our SFRA results, these indicate a high impedance fault on phase B of the low voltage winding. And both the low voltage open circuit and the high voltage to low voltage short circuit test clearly shows this evidence. And what we see in the trace is phase B. Okay, so we know what phase it's on. We know what part of the transformer it is that was damaged from this through fault. Now, I would say this: nobody in their right mind would do anything but tear this transformer down to really see what's going on, and we certainly did, and this was the result. So, my recommendations, and this is important. If you're doing diagnostic testing on a transformer, just as a routine, and you do not have a through fault monitor, I would always include the leakage reactance test in part of your routine. So we're going to do power factor test, we're going to do an excitation test, then we're going to do leakage reactance, both three-phase and per phase, and then your TTR and winding resistance. That is the perfect scenario of testing your transformer. If your leakage reactance test is showing out of the norm, an SFRA should follow. Okay, that's a given. Now, SFRA is really the best method for doing mechanical failure diagnostics, but since it takes so long, you may not always want to have it part of your routine test. Let's say you have a through fault monitor and you haven't noticed any through faults on the system, and it's not a mobile sub that you've been moving from one place to the other. I would say this, that you're probably going to be in pretty good shape, and leakage reactance probably isn't necessary. Okay, but if you do have a through fault monitor and you have had an indication of through faults, okay, regardless of the magnitude or the number of occurrences, then a leakage reactance would be ideal in terms of adding this to your diagnostic testing. Aside from that, equipment that does leakage reactance can also perform a test called frequency response of stray losses, which is a topic for another day, but it's again another diagnostic tool that you can add to your arsenal of maintenance testing that doesn't really involve any longer time or take any more time or add any additional cost to the testing process. So through faults, again, if you have a protective relay system that has a through fault monitor, very important to enable it. And this goes right hand in hand with people that also want to make sure that you enable your sequence of events recorder and your diagnostic uh, events recorder. The worst thing that can happen is that you have an event on the transformer and your differential trips, or your protective relay system trips, and you have no information to go along with that. Okay, if you have a good fault recorder enabled on your relay system and a sequence of events, your protection engineers can actually diagnose whether or not you had a true differential fault, because sometimes differential relays can misoperate. I had an occurrence once where a test technician who commissioned a protective relay on a transformer got a call in the middle of the night because a GSU relay had tripped the unit offline, and by the time he drove out there, the maintenance crews had scaffolding up and had all the mains disconnected and were ready to start testing. And the technician said to the foreman, he said, "Well, have you looked at the fault record, the DFR from the relay?" And he kind of brushed him off and said, "No, go away. We got testing to do on this transformer to find out what was wrong." Well, as it turns out, there was nothing wrong with the relay. It actually nuisance tripped, causing the transformer to come offline, and there was absolutely nothing wrong with the transformer. So through fault monitoring, your DFR and your sequence of events, always make sure that these are enabled and part of your protection system. And this will help your maintenance team, decide what it is they need to do when they perform their maintenance testing. So I am certainly ready to take any questions that you have. I hope this was informative for you.
Thanks, Drew. It was very informative. We have a few questions. One, are these tests done in the field or must they be done in the factory setting?
Well, that's a very good question, and the answer is both. Um, you have to do a short circuit or leakage reactance test at the factory because that's what they do to measure that impedance and stamp it on the nameplate. So yes, that will be done in the factory, but yes, it will also be done in the field, and it should be part of your routine maintenance testing. The same with SFRA. It's very, very important when you specify a new transformer before they load it up and ship it to you. Make sure they get that factory test with the SFRA, that fingerprint, because that's what determines. Otherwise, you have nothing to compare a trace to. You have to have a trace to compare it to, you know, that will show you any kind of deviation if you've had a mechanical failure. So good question, answer both.
Okay, next one. What are the implications of short circuit impedance variations on transformer performance and lifespan?
Well, again, a good question. If you're within plus or minus 3%, both on your three phase and then your per phase, chances are you're in good shape. You will always have a little bit of a variance in the leakage flux in the transformer and the transformer's core, and that's why they give you that 3% tolerance in your measurement. And of course, how you measure, what the external conditions are during the measurement, you can get a little bit of a deviation. But if you have a greater than 3%, either on the three phase or on the per phase, you really want to look for, do further investigation to see if there has been some mechanical failure. And SFRA is going to be your next course of testing. If you see no deviation in your, let's say your leakage reactance was just slightly off on that 3%, but your SFRA came out just fine and didn't show any indication. It may be just that you didn't have all your bushings tied together correctly, or you might want to do it again. But the SFRA is the tell all, right? At that point.
Okay, next question. How does short circuit impedance monitoring help in identifying internal transformer faults?
Well, it's first of all, it's not a monitor because you can't monitor the
Okay.
impedance of the transformer. It's an offline diagnostic test. It has to be
Okay.
disconnected.
Mm-hmm.
Um, but secondly, I'll refer back to that water flowing through the trough. You're going to have some normal leakage in the flux of the transformer, in the core flux of the transformer. And if there's a disruption or a mechanical
Mm-hmm.
movement, okay, it's going to change the impedance characteristic of the transformer windings.
Okay, next one here. How do you calibrate through fault sensors? Reconfirm the accuracy with FDR record?
Hmm. Well, okay, the settings on the through fault have to do with the magnitude, the duration or the length of the fault, and the number of occurrences. Um, how to set that depends on the classification of the transformer and what its manufacturer says is the acceptable mechanical strength. And in other words, they used to say there used to be a guide with transformers. There was always a guide for heating, okay, for electrical withstand of a transformer. Well, now they have also in the specifications of a new transformer the mechanical withstand limits, and that's based on the magnitude of over and above the base rating of the transformer. So if it has a base rating and it says that the manufacturer tells you, well, this can withstand without any possible physical damage 5 times the base rating, Okay, anything over and above that is how you would set your through fault monitor. And again, this information should be available from the manufacturer. If not, there is an IEEE guide that can help you determine what that through fault monitoring should be at. But I mean, even if you're setting, remember, it's not going to trip the transformer offline. It's just going to give you an alarm and record that information. Okay, so if it has been recording through faults, and this happens a lot in distribution circuits, distribution feeders, where you have a transformer feeding a circuit, and you have trees hitting the line all the time, and it's happening continuously. And the through fault monitor may be recording all this and indicating that, hey, you got to do some tree trimming, or you got to find out what's causing all these through faults to happen, without exceeding, greatly exceeding that base rating of the transformer.
Okay, next question. Is demagnetization of the transformer core for residual flux a prerequisite for SFRA?
Yes, absolutely. Yeah, that's very important. And a DMAG should happen before SFRA, by all means.
Is it possible to be done without it?
It depends. If there's magnetizing current in the transformer, it could influence the test, by all means. But yeah, I mean, it's hard to tell whether or not the transformer is magnetized. And this is why we do the one thing that causes the transformer core to be magnetized is your winding resistance test. And that's why we always put that test at the end of the chain of all our dielectric testing.
Right.